Hey, what's up, guys? This is Chung. So today, let's take a look at this one, number 913, cat and mouse. Um, so this one is a very interesting problem because, I think this week we just had like another cat and mouse number two as a weekly in the weekly contest. So I would like to try to explain this one, the first problem for the cat and mouse game. So for this one, like a game, we have like on an undirected graph here, and still we have two players, mouse and cat, and who will plays in turn. So which means that this is another like game theory problem. Okay, and so so at each sorry, so the mouse starts at node one and will move first, and then the cat always starts at node two. And there's also like a hole at node zero. So those are three like a fixed position. And during each player's turn, so they must travel along one edges, which means that they cannot stay still. They have to move in one of the direction. Okay, and additionally, so this is like the conditions that so it's easier to be ignored. So basically, cat cannot move to the hole, which is node zero. And then the game will end in three ways. So the first one is that, if the cat and the mouse are on the same node, then cat wins. And if the mouse reaches the hole first, sorry, since the cat cannot reach the hole, so if the mouse reaches the hole, then the mouse wins. And the third one is like the one that a little bit tricky. So if ever a position is repeated, which means that if any player visits any of the node he has previously visited, then it's gonna be a draw game, and then you need to return 1, 2, or 0 respectively. So that's it. And here we have some examples, right? So this is the graph here, and so for this one, like the mouse starts with here at 1, and the cat starts here. So for this one, we have output 0, which means that this game is going to be a draw game. Why is that? Because so the first time the cat will move to 3, right? And then the cat will move to 5, right? And then the mouse has to move, and then he will move the mouse will move to 4, and then the cat will move back to 2. So and then the mouse come back here, and then the cat will come back here. So gonna re move repeatedly, so which means that this is going to be a draw game. The cat, basically the mouse cannot reach the hole, and but the cat cannot catch the mouse either. So here's another example, right? So here we have a mouse at here and a cat at here, obviously, right? So the mouse would reach the hole directly without being caught by the cat. Yeah, there's some like constraints here. So, I mean, for this kind of like game theory problem, the I think one of the common strategies do a DFS, right? So we have a DFS with actually it's a like top-down DP. And we have some state, and at each of the at each turn, the players will play out optimally. So in this case, like basically, so when I say the players will always play optimally, they will always try to win, right? So in case of the mouse, right? If any of the basically from one of the state, they will have like many other states here, right? So if any of those states can give the current player a win, then the current player will definitely go to that state, okay? And vice versa, right? So if that state will give the current player a lose. The current player, basically, it will definitely not go in that's that scenario. It will try other scenarios until there's nothing. I mean, so another scenario is that like if all the scenarios there will be always a lose, and then the current player has to return a lose, right? So that's for the case of win or lose. But for this one, we have like we have a draw case. That's gonna be a more difficult. And you can try to maintain like a visited nodes along the way, but that's gonna be very hard to implement. And another another way of handling this draw case is we can, instead of, basically we have a DP here. So the first one is going to be the mouse, right? And second one is going to be the cat. So for the third one, what we can do is that we can introduce another a third state, which is the current moves. And I mean, if the moves is greater than the total nodes, then the 2 times the nodes, then we can return 0. So it means that, whenever the moves is greater than the 2 times the number of nodes, then we're saying that there must have already been a move that has already been visited. Sorry, there must have already been a move that have visited a node that previously visited already. Because why is that? Let's say we have a node, right? So since two players will take no will make the move in turns. So to visit each of the nodes once, it will need uh, uh, nodes moves. But if the nodes moves have already is already be greater than the 2 times the nodes, then there has to be a player that has already visited a previously visited nodes. That's why we can return a 0. And so for this part, I mean, I'm not 100% confident about the this upper bound, but I think with this kind of uh, description here, I believe it's safe for us to use this condition to return a 0. So yeah, and basically that's gonna be the idea of the top-down uh, DP solution, right? And so besides the top-down DP, actually for this kind of game theory problem, uh, so for this one, it also introduced like a bottom-up solutions, where I'll explain later on. So, but let me try to implement the first one, which is the top-down DP. So we have a DP. The first one is the mouse, right? And then we have a cat. Let's mouse, cat, and moves, and then we're gonna have like the LRU of cache, right? None. So for the exit point, like I said, if the moves is equal to the length of the graph times 2, right? So if this one is greater, let's see a greater, right? Then we return 0. And if the mouse is equal to the cat, then cat wins, which means we're gonna return 2. Or the mouse is equal to 0, then we return 0. We return 1, which means the mouse wins. So now let's handle the scenarios separately, which means that, the first one is the mouse turn. So we just use this one if the moves divided by 2 equals to 0, right? That's going to be the mouse turn, because in the end, what we're going to do is we simply return a DP of 1, 2, and 0. So the moves, and then what we can do here. So like I said, we have neighbors, right? Neighbors in graph of the mouse. So we have answer, right? So the answer is going to be the DP of the neighbors, right? And then the cat dot, and then we have a moves +1. That's going to be the recursive DP call, right? So now we have a new position for the mouse, but the cat stays the same. Basically, so if the answer is equal to 1, it means that 1 means the mouse wins. So if the current one is the mouse turn, and there's a there's a next step scenario that the mouse can win, the mouse will definitely go to that direction, which means that we're going to return 1, right? And then in the end, I mean, if nothing wins, there's no win, then we can return 2. But like I said, this is only the win or lose case. But in this case, we have like what? We have a draw case, which is a 0, which means that, before returning 2, and so what does it mean? It means that, let's say there's no winning scenario for mouse, but before returning, before admitting a lose, let's check if there's any scenario can give us a draw, because draw is better than losing the game. So that's why, here I'm going to create like a flag. I'm going to call it can't draw, right? At the beginning, it's going to be the false. So basically, I check if the answer is equal to 0. So if in any of the scenarios we can get a draw, then I'll mark this one can draw equals to true. So in the end, before returning false, I'm going to check if the can draw is true. Then rather than uh, being defeated, I'm okay to make this to make a draw game. Else return 2. Okay. Yeah. So that's that. And now the second one is basically it's the cat's turn, right? Similarly, right? So I think it's pretty much the same. I'll just copy and paste here. Instead, we're gonna use the cat, right, to get the neighbors. So here the mouse will stay the same, but we're gonna have like a new cat coordinates. So here, similar for I'm going to do answer equal to 2, which means that if the cat can win, so the cat will definitely go that direction, right? Otherwise, I'm also going to do like a draw check here. So here, instead, in the end, I'm returning uh, a 1 in the end. Yep, I think that's it. So let's try to run the code. Oh, did I? Uh, line 16. Oh, sorry. C. Yeah. Mm. Excuse me. So did I make any mistake here? So we have this one. If this one is 0, it can draw neighbors is that cats. Turns out 2 cats. Yeah, I think everything looks okay to me. Oh, did I? Is this the one? Hmm. Let me check. Yeah, I remember that there's like a condition, right? Additionally, so you, cat is not allowed to travel to the hole. So which means that, here, while looping through the neighbors for the next new move for the cat, we need to check that. Basically, if the neighbor is equal to 0, we simply do a continue. Yeah, okay. Yep, so this time it works. Mm, yep. And so for the time and space complexity, right, I think so we have like, what's going to be the n? So let's say the n is the length of the graphs, basically the length of the nodes. We have like n times n times another n here, right? Basically, that's going to be the moves of the. This is also the n, so it's going to be another n. So I think somewhere, I think close to n cube. I mean, even though we have another like for loop here, right, inside of the DP here, but this one is bounded to the structure of the moves here. So which means that if we have more moves and this neighbor will be less. I mean, basically this one is not always going to be a n because and it depends on depend on the structure of the graphs here. So yeah, I would say the time complexity is still close to the n cube. Yeah. So that's going to be the first approach, which is the traditional top-down DP solutions. Basically, so this is like another like classic game theory problem, where we just handle each of the players separately, and for each of the player, we always play optimally, right? So if there's a like a winning strategy, the player will definitely go with that. Otherwise, it will go to the second best option, which is the draw game, and the last one is the lose. Cool. So that's the first approach. And for this kind of problem, like I said, instead of the top down, there's like another way to solve this problem, which is the bottom up. So what does the bottom up means? It means that we process the states from the end instead of from the beginning. So but so processing from the end means that we have some states that we know who will win eventually. So basically, here are the states we know that either the cat will win or the mouse will win, and we know all the states for those kind of conditions. And the problem is that and so from this kind of certain win or lose state, we can we can go to the previously state, and we can get the result for the previously state, right? So which means that let's say I'm gonna give you an example. So let's say we have a MC, and then we have like the turn. So let's say the turn is the mouse. So let's say the this MC1 is a state. So one means it's the mouse turn, and two means it's the cat's turn. So let's say for this state, we know this one the result is 2. 2 means that for this state, I mean it's mouse turn to move, and the cat will win based on this state. Then what can we get? So I mean remember, so this is the final state, and there are like many states can go to the current can go to this state. And since this one is the mouse turn, so which means that the previously state must be the cat's turn. And since the winning state, so since the result for this state is the other one, is the other player's win, so we can just certainly deduce we have another state like m dot c2, and then c2 dot 2, and here we have a m dot c3 dot 2, and then we have a m dot c4 dot 2. So all these states, their their result are also going to be 2, which means that at this state the cat will definitely win because there's like a neighbor, right, which will be the next state that can guarantee a win for the cat, so that at all these kind of parents or the previously states, the cat will definitely choose this state. Similarly, for the if this one is 2 and the result is 1, so in this case the turn is cat. So the current turn is cat, but the result is the mouse will win. So for this one, it's going to be a different scenario, but similarly, right? In the previously state, so all the states going to be the mouse state, right? And then for all those kind of mouse state, they're always going to be 1 instead of 2. Because similarly, because the mouse will definitely choose the scenario because the mouse know the next state, there's a state that can give the mouse a win. So, and that's basically the idea, right, for this bottom up. And so basically we start with the known either win or lose state, and we just try to populate all the states from bottom up, and then in the end the states that we didn't get to populate will be the draw state. And then after this kind of a bottom up populates, we can simply return we can certainly check the starting state, which is the 1, 2, and 1. If this one has been populated or not. If it is, then that value is going to be our value. Otherwise, it's going to be a 0. Okay. So let's try to implement that one. So the second implementation is a little bit long. And so to store the to store the process as a result, I'm going to use like a dictionary to store that. And so the key will be what? The key will be the mouse, the cat, and the turn. Okay, and the value will be basically will be the result, right? So the result either 0, 1, or 2. Since we have like a default dictionary, the integer, so if we don't populate it, so the default value will be 0, which is the draw, right? Otherwise, it's going to be either 1 or 2. So, and then we can start with the known like ending states, right? And then I'm gonna use like the queue to do you can call it the BFS search. And so what are the known states that's gonna can certainly guaranteeing that either like the mouse win or the cat will win. So it's these 2 states. And since we have another state which is a turn, that's why we also need to do a for loop for that in range of 1, 2, 3. So that's the outer loop. So for all the for both the mouse or the cat's turn, we loop through from 1 to n. So the reason we do a 1 to n is because the cat cannot go to the zero nodes. So the first one is the uh, mouse win, right? It's going to be the results of the of 0, I, and t, which is going to be 1. So here I'm doing the so for all the so the winning state for the mouse is going to be the 0, right? And then the cat could be anywhere, and the turn could be either the mouse turn or the cat's turn. And then I'm going to add this one to the queue so that we can start the BFS search from this state backwards. And so 0, I, and t. Similar for the cat win, right? So for cat win, it's going to be I, t, right? So this means that cat and the mouse, they're on the same nodes. Again, right? Since we are doing from 1 to n, we're guaranteeing that the cat will never go to the 0 node. And then we're gonna also append this one to the queue. Cool. So now we have the starting state, and we just need to do a while queue, right? To do this, basically, for this one we have sorry, m dot c dot turn, right? It's going to be a q dot pop left. So basically, we try to from the current state, we're trying to process trying to deduce, to populate, update the next states, or you can call it a previously state. And then in the end, right, we can just we simply just return the results of 1, 2, and 1. So here, the reason I use like 1 and 2 and 0 is because we have a 0 state for the draw game. And so for the turn, instead of the reason I use the 1 and the 2 to represent the mouse turn and the cat's turn instead of 0 and 1, like the what we have from the top-down DP solution, is because um, by using 1 and 2 later on, it's going to be easier for us to map that value into the final result. I'll show you what I mean later soon. So, and now since we have this MC and T, we can get the results, right, for this kind of states first. It's going to be M dot C dot T. Okay. So from the current state, from the current node or the current state, we need to get all the parent state. So it's going to be a m2.c2.t2, right? In get pre-nodes, states, right? m.c.t. Right. So from this state, we can get the previously states from the current states by using the graph. Okay. And and then we have a R2 equals to the result, right? The M2, C2, and the T2. So we need to do a check here. Basically, if the R2 is greater than 0, which means that this state has already been processed before, so that we just need to do a continue. We just simply skip that. Now let's populate, right? Populate next previously state. So the first one is the what? It's the one I just showed you, right? The basically and if the t2 is equal to r, so which means that uh, or we can use this. Like I said, we have like the m dot c dot 1. That's the state. If the result for the state is equal to 2, right? Then we okay. So I think maybe we can use that. So and if the r is equal to the 3 minus t. So that's why like I said, so for the turn instead of using 0 and 1, I use 1. Basically, if the turn and the result for the previous state they're different, right? So it means that for the mouse turn, uh, the cat will win, and if it's a cat's turn, the mouse will win. So for this one, for this case, we can make sure that this previous state is gonna be a guaranteed win, right? Result's gonna be m2 c2 t2. It's gonna be the same as the r here. And then since we already populate that one, we also need to add this one to the queue so that we can use this state later on, right? To populate more state. Okay, so that's that one. And oh yeah, so for the previously states method, so let's implement that one real quick. Get pre states, right? So we have m.c.t. So it's going to be the answer of a list, and basically if the t is equal to 1, right, then it means that the current state is t. So sorry, so the current state is mouse, so which means that the previous state is cat, which means that we need to loop through the edges, the neighbors for the graph from the cat. Okay, and so here's a small things we need to be careful is that always remember any time when we try to loop through the neighbors for a cat, we need always to check, right? If the c2 is equal to 0, we continue, right? Otherwise we just dot append that state. It's going to be a m dot c2 dot 2, right? It's going to be the previously state. And similarly for the if the current turn is cat, so which means we need to loop through the mouse neighbor, maybe m. Then for the mouse, there's no need to check the 0 because mouse can go anywhere. And so now we have like the mouse 2, c, and 1. Okay, so that's gonna be the state the method here. Okay, so what's next? And let's see. I think here we're only handling one of the scenarios here, because this one will always can always win, right? So So this case I already explained, right? So that's the case, for example, if the current current turn is the mouse, but the result is the cat's win. That's we can directly populate that. What if the current turn is the mouse, but it's the instead of the cat's win, it's the mouse win. Similarly, for the m.c.2 equals to 2, right? These two are like very similar. Let's say for this one, if the current state turn is the mouse turn, but it's for the current state, the mouse will win. Then what's gonna happen for the previously state, which is gonna be the cat state, right? For example, we have like m dot c2 dot 2, right? That this is gonna be the one of the previously state. We could have multiple states, right? But let's consider this one state. So if that's the case, since I mean from this state, the cat would definitely not go into this state because he knows that if he goes to this state, then the mouse will win. So what he will do here, so the cat will try to explore another state, right? And when can we update the results for this state, right? I think that's gonna be a similar with a game theory, right? If all the neighbor states from the states they're always giving like a 1 as a result, then the cat at this state has no other options but to set to 1. So remember, so for the current for the bottom up, we're not considering draw draw cases. We're only considering either mouse will win or the cat will win. Cool. So that's why for the second one, right, we need to check. And so basically, since we already checked this one, so which means that we already covered the first scenario. So at this scenario, at the second, at this else if here, it means that so it's either this case or this case, which means that the result and the turn they are the same. So if that's the case, we just need to check if our next moves failed from the M2, C2, and T2. And then if that's the case, like, right, if the current state, if all the next move there is failed, then we have to set the results for this kind of state to be the 3 minus T2, which means that the turn has to be basically and if it is the cat's turn, right? If it is the mouse turn, then the uh, the cat will win. If it's a cat's turn, then the mouse will win. That's why we do a 3 minus T2 as a shortcut. All right. Similarly, we also need to add this one to the append. Same thing, right? So to the queue. Okay, so and now let's try to implement the last helper functions, which is this one. Okay, so we have a m.c.t. So for this one, what we're trying to accomplish is that we want to know if all the mm, if all the neighbors, right? If all the neighbors are a losing state. So which, let's say if it is a if it's a mouse turn, okay, if it's a mouse turn, then so the next state, right? Remember, so here we are like uh, going from the current state to the next state. It's gonna be since it's mouse turn, so the next move is gonna be the mouse, right? Graph.m, and so if the results of the next state is gonna be m2.c.2, right? It's not equal to 2, then we return false. So this one is saying that if the next state is not a cat's win, then then basically it's not all the next moves is failed, right? Because this one is true if the next moves are all gonna be a wins for cat, then that's gonna be the true. Otherwise, we return false, right? Similarly, for this one, like we do a for C2 in graph of C, right? Again, right? Don't forget to skip this zero node case, and then if the results of this, so for this one, it's going to be the m.c2.1, right? It's not equal, that's not equal to 1, then we also return false. Otherwise, in the end, we return true. Yep. Yeah, I think that's it. And that's the whole implementation, I believe. And let's try to run the code here. None type, line 90. Oh, I must have forgotten to return this answer here. Yeah. Okay, let's see. Did I do anything wrong here? Okay, so the because to continue, okay. And C2 MC, so this one looks good. So we have M2 equals to that, results M2. Uh, yes, sorry, this is a long implementation, so it's gonna be a little bit hard to debug here. Trying to check this thing. One, oh, here, 2, right? Cat's win means the 2. Okay, submit. All right, great. So it's accepted. Yeah, so basically that's the second implementation. So for second one, I believe the time complexity are the same since the we have n square state, right? And for the n square state, that's going to be the since the t is like a constant, that's why the m times c is going to be n square. And then for each of the state here, we're doing like a for loop here, right? We have a for loop for the previously states. It's going to be another n here. Yeah, and yeah, so that's why it's going to be an n cube. And actually, we have like uh, another nested for loop here. I believe here we're also having like another for loop, right? To check the parent nodes here or the next nodes. And so actually, to be honest, so this one's gonna be a n to the power of 4. Yeah, in my opinion. I mean, even though I believe we can improve this part by not always checking out all the neighbors, we can just create a global uh, or degree or like edge list that every time once we are process one of the edges, we'll decrease the degree for that. So that's and here we can only do a O1 check. So ideally, if we do it that way or do it so this one, the time compressive for the second one should also be a n cube. Yeah, but I didn't do it because this is the most intuitive way to show you guys the the idea here. Okay, so just to recap real quick, right? So for the second bottom-up solution, we start by populating the known winning state for both the mouse and the cat, and then from there, right, we do a BFS search. We try to populate the next states, and which we have two scenarios. The first one is a direct win. The second one is basically it's a indirect lose, right? To be able to lose for the state, all the neighbors has to be a lose, and then we can set the current state to a losing value. And otherwise, all the rest they're considered to be a draw state. That's why, in the end we simply check the results for this state, for the starting state. Cool. I think this is gonna be this video is long enough, and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.